Hi, friends. There's a lot of news out there. Most of it's not so good, but there's a lot of news out there, and it's really good. A long time ago, I sat down to make a list of things not to worry about. I thought I had a lot on my plate and figured the list of things not to worry about would be shorter and easier to make than the ones to worry about. And I was directed to John and some of the statements Jesus made where he uses the phrase, I am. The biggest one in chapter 8. Jesus is talking to some Jews, and he makes a statement in which he basically claims to be God. They didn't like that, but they knew what he was trying to say. But there are a bunch of other I am statements that are really, really good news. For example, Jesus says, I am the bread of life, and therefore, if we're his children, we never need to worry about going spiritually hungry or thirsty. Jesus says, I am the light of the world, and so his followers never need to be afraid of the dark. Jesus says, I am the gate, and so we don't need to be worried about getting locked out of our house. Jesus says, I am the good shepherd, so we never need to worry about getting lost. Jesus said, I'm the resurrection and the life, and so really we don't need to worry about death at all. Jesus said, I am the vine, and you are the branches, and so we never need to worry about that human feeling that wonders if our life really is significant. If we're a believer, our life will bear fruit. We are important. This PowerPoint is over Eve's chapter 12, the first part. So it's dealing with the 18th century or the 1700s, early part of that century. And the things that I want to do are talk about a branch of mathematics called analysis that was starting to develop in these times, to give some examples of how calculus was applied to the sciences especially, and then to talk about a few mathematicians, important mathematicians of the period, most notably Leonhard Euler. First of all, regarding analysis. So here is my kind of nutshell of how math could have been organized in the 1700s. If we go back in history, long before we have written history, people were doing arithmetic. You have to know what happens when you have 5 sheep and one of them die, and so on. And people were doing measurement. So this is my field, that's your field, here's the boundary line, and so on. And then over time, arithmetic generalized to become algebra. So people discovered, hey, you can do more than add and subtract numbers. You can add and subtract, say, polynomials and lots of other things as well. And people generalized measurement to geometry. So instead of just talking about distances and so on, we can talk about Pythagorean theorem and lots of other interesting relationships. Then, around the time of Newton and Leibniz, people started talking about a branch of mathematics, which later came to be known as calculus, having mostly to do with functions and how they change. So there's an input and an output. You change the input, how fast does the output change? That kind of thing. You've done lots of that before. And then over time, people generalized calculus to be a broader branch of mathematics now called analysis. I've drawn these non-overlapping, but in reality, each of these two connect with each other. So for example, what we talked about, connections between algebra and geometry, so-called analytic geometry, and there are other connections as well, and other branches of mathematics by now as well. But that's kind of the place of calculus in the history up to that point. And Eves points out that the development of calculus and then generalizing into analysis kind of follows 4 centuries here. In the 1600s, in Newton and Leibniz time, calculus was developed. In the 1700s, it was a century of applications of calculus, more than anything else to physics, people doing problems in mechanics and optics and so on. but also in mathematics, people were starting to write and solve differential equations, to do optimization, so not to just find maxima and minima of a simple function, but Calc 3 kind of problems and so on, and also approximation, representing functions with Taylor series and so on. Then in the 1800s, was kind of a time to go back and lay the theory. People were using calculus but didn't necessarily know why it worked. So in the 1800s, the idea of a limit and infinite sets were developed. If you've taken and enjoyed a course called Real Analysis, that's primarily what we're talking about. Or maybe you'll yet take and enjoy a course called Real Analysis. And then in the 1900s, a generalization of calculus to be full-blown what we call analysis. And there are many, many branches of analysis now. So going back into the 17th century, some important people and their discoveries. The infamous Bernoulli brothers, two brothers and actually some of their sons as well, who worked together and fought, and it was quite a good story. Some of the things that happened in this time, the development of polar coordinates. So instead of representing things in a rectangular grid with XY coordinates, you've seen in Calc 2 and earlier classes, we can represent points in r theta notation, and sometimes that's much easier to describe curves that way. Things that are named after them, the Bernoulli probability distribution, where a random variable can either be a success or a failure. And this is the backbone of what we call the binomial distribution, which is one of the most important distributions in probability. There's a fluid equation from the Bernoullis, and fluid is flowing through a pipe, and the pipe gets wider and narrower and so on, and there's a relationship between the fluid flow and the pressure and so on. So very important in physics. And maybe most important of all, as much as anyone, they're responsible for the development of a branch of mathematics called the calculus of variations, which is helpful in solving optimization problems. For example, suppose we have a particle here, and down is down on the graph. Down is the direction that gravity points. So the gravity is trying to pull you down. We want the particle to go from here to here. And we have a choice of many paths. We could build a straight line path and just let the thing roll down this slope, or we could curve it a little bit and let it roll along the red line or the blue or the green curve. And the question is, which of these curves should we pick so that the particle gets from this point to this point in the shortest amount of time? And it turns out that it's the blue curve on this picture, which is our friend the cycloid that we've seen before. So it's hard enough to think of discovering this, but the Bernoullis were able to prove that this curve gives the fastest travel. Abraham de Moivre was another gentleman of this time. He was involved heavily in probability, and perhaps the first person to take these mathematics of probability and start to do actuarial science. So the mathematics of risk and predicting risk, especially having to do with natural disasters and things like that. You may have colleagues in your classes who are planning to be actuaries, and their discipline goes back to this time. And another important thing that he's famous for is de Moivre's theorem, which is an important result in analytic trigonometry. If we look at the blue section here first, if I have a complex number and I want to raise it to a power, one way is brute force. So FOIL, 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 and simplify as you go. But de Moivre discovered that if you write the complex number in so-called polar form, having to do with this polar coordinates, then to calculate the nth power, it's a simple calculation of raising a real number to a power and multiplying an angle by that number. So the level of simplification here is sort of analogous to using logarithms to change multiplication into addition. An incredible computational simplification and very important in physics and engineering. Taylor and Maclaurin didn't really work together, but kind of on the same problems. So from Calc 2, you may remember this friend or this foe, depending on what you think of it. But I can represent a function as a number plus a number times power of x plus a number times power of x squared plus number of times power of x cubed and so on. And the contribution of Taylor is that we know how to calculate these things. We should differentiate the function, plug in this x sub 0, the point at which we're trying to near which we're trying to approximate the function, divide by the factorial of the term, and then this is an infinite series, but we can cut it off wherever we want and just use the first few terms, which are a polynomial, to approximate any function. People have been doing that before, but this turned it into a science. Now, no matter what function you're talking about, e to the x, all right, apply the formula, here's the power series for e to the x. Sine, all right, here's the power series for sine. Cosine for cosine, and so on. So any function that's differentiable now can be written as a Taylor series, and then by truncating the series, we can do approximations. And certainly not least, Leonhard Euler, one of the top 3 or 4 mathematicians of all time. So let's spend a little time here and talk about him. Truly a mathematician of the 1700s and roughly a contemporary with, say, George Washington. So we're getting into a time period when we might be able to relate a little better to these people. Nice guy. Euler was a preacher's kid. And this is not what made him nice, but he was nice in bearing with it. He went blind in one eye at age 31, and it was the right eye, by the way, so if you see him in a picture, he almost always puts his right eye away from the portrait. Then went blind in his left eye at age 59, and since you only have 2 eyes, that means he's nearly totally blind for the latter part of his life, 15 years or so. Fathered 13 children, only 5 of them survived through childhood, so acquainted with grief, but not unusual for that time period when hygiene was such a problem. By all accounts, truly a nice man, gentle, humble, was involved in the raising of his children, unlike some of the people we've talked about who were geniuses but real bears to get along with. Euler seems to be a nice guy. He was also a devout Christian, and then he spent most of his life doing mathematics, but along the way, German was his native language. Then he also learned French, Latin, Greek, Hebrew, Russian, and English. Latin, Greek, and Hebrew. Latin because the educated people of the day wrote in Latin, and Greek and Hebrew because presumably he's a Christian and wants to be able to study the Bible. What about Euler's work in totality? He wrote more papers than any other mathematician in history, at least before the 20th century and probably still. Wrote in Latin, so too bad for those of us who don't read Latin and would like to look at his original works, but they've been translated. Now, amazing fact, this guy is totally blind for the last 15 years of his life. Meanwhile, he's writing 1 mathematical paper a week on average during at least one of these years. So he can't see. He has the first 100 prime numbers and their squares, cubes, 4th powers, and so on, all memorized. He dictates to his secretary, who writes down these papers, and then as soon as he finishes one, he goes on to something completely different, and these papers just stack up. So he wrote papers in almost every area of mathematics, and some of them weren't published until decades after he died. He just wrote so many that the journals couldn't print them all. He didn't just write mathematical research papers, he also wrote elementary textbooks, and more than anybody else, Euler is probably responsible for our modern notation, at least for the notation that appears in our calculus book. So he's the first guy who writes f of x in a function notation. He uses e for the base of the natural exponential. He uses I for the imaginary number. He uses pi for the ratio of the circumference to the diameter. So we've talked about pi for a long time, but Euler is the first person to use this letter to represent this. He uses sigma for a summation. And because he wrote so many papers, and in particular because he wrote textbooks, and because he was careful and consistent about the notation he chose, it stuck. So other than the Latin part, we might be able to read his papers finally. And some results of Euler, just to give a feel for the kinds of things he was involved in. He has this so-called Euler's formula. So I is square root of -1, e is the base, natural exponential base. E to the ix equals cosine x plus I times sine x. Bizarre and amazing result. Why is this thing even defined, and so on, and then why should it be equal? Why should an exponential relate to cosines and sines? If you doubt this, then the way to do it is to go back to Euler's formulas for the Taylor series for e to the x and for cosine of x and for sine of x, and show that it actually works even when we have an imaginary number in it. Euler's line of a triangle. This is totally bizarre but neat. So let's see. Euler's line is the red line, and it's the line that goes through 4 different points related to a triangle. What are they? Well, if we take the centroid of the triangle, that's to take each vertex and join it to the midpoint of the opposite side. Those 3 intersect in a point called the centroid. Then the orthocenter. So if we take each vertex and drop a perpendicular to the opposite side, the intersection of those 3 points is called the orthocenter. If we take each side and construct the perpendicular bisector, those 3 intersect in the green point called the circumcenter, and then there's something called the 9-point circle, and its center is in red. And Euler says and proves that all 4 of these points are on the same line called the Euler line. It's just totally amazing and bizarre. I would work with this for 1,000,000 years and never even notice this fact, and Euler discovers it, proves it, and moves on the next week to something else. See, from discrete math, you may remember something called Euler circuits. And it started with a problem where people in this town of Königsberg wanted to know if there's a way to go across each bridge exactly once. And not a particularly practical problem or something that you would need to know, but an interesting math problem. And Euler basically invents graph theory to start studying things like this. Another of his results from graph theory is his formula relating the number of vertices and edges and faces of a convex polyhedron. So here are some regular solids, but it holds for irregular solids too, as long as they're convex, that number of vertices minus number of edges plus number of faces is always equal to 2. From transitions, you may remember Euler's phi function or totient function. I have a positive integer and I count the number of integers less than n that are relatively prime to n. That's called the totient function. And then Euler has a result that if 2 numbers a and n are relatively prime, then a to the phi of n is congruent to 1 mod n. Very important result in number theory. And we'll stop there.